Okay, so here we are reviewing some very important basics and acidic concepts of acid-base unit through this worksheet. And this worksheet comprehensively reviews just about everything you will see on your test. And it is a little challenging, so I'm making it a review worksheet, and I will have the key posted. But you may want to hear me walk yourself through, or hear me walk you through some of these questions. In any case, let's get started. Talking about electrolytes, and we learned already that electrolytes are anything that in solution make free ions. Okay, and we learned that things that make free ions, for the most part, are soluble salts. So soluble salts, like for instance, let's say sodium chloride, that's going to break apart into Na plus and Cl negative. Okay, this solid breaks apart into these aqueous ions. Okay, and these ions, which have molecule ion attractions with the water, are free to actually be attracted to a negative or a positive, and these ions can flow through the solution if there is a charge to conduct a charge. But, okay, there are other compounds that make free ions, and they of course are acids, okay, and bases. Okay, acids, on the simplest definition, produce protons. Now in truth, in solution, they make hydronium ions, okay, but they're ions nonetheless. And also, they have their conjugate bases, okay, that are charged, okay, usually negative. So if you have an acid, HA, it breaks apart into an H plus and an A negative in solution. There's your free ions. And of course, bases do the same thing. Bases either pull a proton from a chemical to create a charged complex, or they themselves producing hydroxides in solution. Either way, acids and bases create ions that are free to move and be mobile throughout a solution or a homogeneous mixture, and these ions are free to conduct a charge. So our new definition of acids and base electrolytes are salts that are soluble, acids, and bases. So the question is, who is a soluble salt and who is an acid and base? So I look at my first question. Here is A, and this is nitric acid. Okay, it's the nitrate ion. So 8 becomes 6. So that is a top 5 acid right there. So that is definitely going to be an acid. Okay, I look at B. I know that CO2 is listed on, I believe, table K as acids. Okay, and we should know that CO2 plus water makes carbonic acid, but CO2 is a Lewis acid because it is an acceptor of a lone pair by the water. Okay, we went over that. In fact, I had dry ice, okay, CO2 solid in water, and we noticed that the pH dropped with my indicators, and you make, carbonic acid, okay, in truth, that will dissociate to make H plus and the bicarbonate ion, also called a hydrogen carbonate ion. But you should know that this is accepting a lone pair, and we talked about that. So the CO2, and it's listed in your reference table. Okay, let's look at the F negative ion. The F negative ion. How can I know if that's an acid, base, or a salt? Well, I'll tell you what. I don't have to, because, well, this F negative ion is an ion, and it's aqueous, so it's a free ion. So that is going to be, okay, a compound I list. But the F negative ion is also a base. Now, why is it a base? Well, the F negative ion has an ability in water to extract a proton from the H to make HF and the hydroxide. Now, Mr. Gratsky, how do I know that it does that? Well, I know that it does that because anything negative that's not a conjugate base of a strong acid has that ability. Okay, so let's go to table L for a second. Okay, now getting back here to this table L that I call, but it's nothing more than a list of Kas for acids, so it's giving me the relative strength of acids here. But if you look closely, the top 5 acids listed here, and we're missing 2 for the 7 total strong acids, we learn that these are completely dissociating, which means their Kas, which are what? The products over reactants, are favored at equilibrium. Very little reactants. So these numbers are getting very, very large, approaching infinity. All right, so this is the strongest of all the acids in this table, okay? Now, their conjugate bases, which by the Bronson-Lowry definition is the ability to accept a proton, is limited at best. In fact, almost insignificant that when you count their ability to go backwards. I negative, Br negative, Cl negative, nitrate, hydrogen sulfate, these guys almost have no ability to accept the proton to reform the acid. That's why the equilibrium position rests in favor of the products. So these are the weakest conjugate bases. So if you had these ions floating in your water, they would not be able to yank a proton off of water. So any other ion that is negatively charged besides the top 5 acids that I'm giving you for this course, okay, have an ability. So because HF is a weak acid, it barely dissociates. Its Ka is so small that its reactants are definitely favored. So very little. So that means that if the equilibrium position is favored toward the reactant side by a small equilibrium constant, then that means F has a great ability to form or yank a proton away from water. So back here, we have, as long as you have an ion, okay, that's negative and is not one of the conjugate bases of the top 5 strong acids, okay, you've got yourself a base. So F negative is a ion that's an electrolyte just because it is an ion, but it's also a base in the sense that it has the ability. So anything, any salt that has a conjugate base of a negative ion that's not one of the top 5 listed would be a base. Okay? For instance, let's look at E. E is sodium carbonate. Now, sodium carbonate breaks apart into 2 sodium ions, and that itself would be electrolyte. You consider this to be a salt. Okay? So this itself would be an electrolyte without even thinking about it as an acid or base, because this is a salt that breaks apart into ions. But as we get more questions about, hey, is this an acidic or a basic salt? Look at the ion. CO3 negative 2. Well, is this a conjugate base of any of the top 5 acids I've given you? No, it's not. So this has an ability to yank protons from water. And that word, that phrase I use is, it can ionize water. And if it does so, it's going to produce that hydroxide ion and make ions in solution. Now, in truth, this is a salt, but this is a basic salt because it has an ion in it that can extract protons from water and create the hydroxide. It's also a salt, okay, that in itself would be an electrolyte because of the group 1 ion makes it soluble. So I'm going to circle it as a base, but it's really a salt, okay? Let's continue down this path. Let me get some stuff out of the way here. So what about, as we go in order, barium hydroxide? Well, barium hydroxide is one of our strong bases. It's a salt, okay, that actually produces hydroxides. So obviously I'm going to put D here. We're going to put E here because it's salt that is basic. And then I look here, potassium nitrate. Now this is also a salt. It's a metal and a nonmetal, okay? It's a metal and a polyatomic ion, the nitrate ion. So it of course dissociates to K+, NO3. It's famously called saltpeter. And in any case, gunpowder is made with this. In any case, this is a salt that's very soluble, and we've dealt with this in lab. We had a solubility curve lab. So this is definitely electrolyte. And I'm going to put this down as F, and I'm changing the colors here. So this is definitely a neutral salt. This salt is not an acid or base. Okay, now why do I say that? I say that because the K+ we know that group 1 ions never ionize water because they're just soluble. They're most of the time spectator. They're just too big. Their charge density is too small to yank an electron. Okay? Nitrate ions. Well, we know that nitrate ions also very soluble, and their charge density is so low. And my friends in chemistry, nitrate is the conjugate base of what? Nitric acid, HNO3. The reason why nitric acid is a strong acid is because it has the ability to dissociate or completely, or you can think of the conjugate base has no ability to reform the acid and pluck a proton from water. So that's how I'm looking at these compounds, as you should be. So KNO3 is definitely an electrolyte. Okay? Now, let's look at G. This is a complex, as we talked about. This is the iron plus 2 small ion, high charge density that's pulling in a lone pair from water, and 6 of them. Okay, and you should know that, well, G would be a electrolyte just because it's a charge. Anything with a charge in solution would conduct a charge in that solution and be electrolyte. But I'm going to write G as an acid. I'm writing red for acid if you haven't noticed, okay, because I remembered teaching you that this high charge density pulls this pair of electrons and makes it drift toward the iron plus 2, which further makes this H be electron deficient and become sloughed off as an H plus. So metals, okay, that have these complexes, that can form these complexes because their charge density is so high, mostly transitional metals, okay, because they have multiple oxidation states and are typically starting out smaller than our reactive group 1 and group 2 metals can do this. And as a reminder, we have these, okay, on our reference table, okay. So if you go to the table L that I've been giving you, you'll see a couple given to you. And as we scroll down, you'll see some examples, and there's actually the actual examples listed right there. So looking at table L, I can see that this has a Ka, which means there is some acidity. The H plus is given off. Not a strong acid, but significant. And I think we did copper in class. All right, look at aluminum. Here's another complex. Okay, so there's an example of some complexes where the transitional metal is attracting 6 waters. And for those that remember, the reason why it's 6 waters is because it makes a very stable octahedral complex. Okay? So G is clearly going to be, okay, one of our electrolytes because it's an acid and it's also an ion, okay? It's positive in itself and it's also an acid. So it produces ions and itself is an ion in solution. It will conduct a charge. Okay, H. Looking at H here, it's sodium acetate. This is the acetate ion right here. The question is this salt acidic or basic? Well, C2H3O2 is the acetate ion. It's negative. And if you haven't figured this out, well, if you add a proton to it, H plus, it gets rid of that negative. This is hydrogen acetate, or if you remember the naming system, this is acetic acid, right? The acetate ion, 8 becomes ic. So this becomes acetic acid. This is vinegar. Okay? Wow, so sodium acetate. Now we know the sodium becomes Na+, and all group 1 ions have no ability to pluck an H off. Well, why? They're too big. In fact, that's why they make strong bases. Strong bases are what? Salts, in a special case, that break apart into positives and negatives. Okay? So this doesn't do anything. It's too big. This, of course, is our what makes the base, the pH rise. So in any case, the acetate ion, if you haven't figured it out, is the conjugate base of acetic acid. Is acetic acid a strong acid? And the answer, of course, is no. It's not one of the top 5. If you're not sure, you'll always have that table L for our quiz and test. And it's not a strong acid. Okay? So therefore, you know that its conjugate base is significant. Its Kb is significant, which means this, if you were to drop sodium acetate and produce the acetate ion in solution, what would happen is this is a pretty strong conjugate base. Weak acid, pretty strong conjugate base, which has an ability to pluck an H from water, or as I keep saying, it can ionize water. And it can reform the acid, and when it does so, it leaves the water as a hydroxide, making an ion. Okay? So, for 2 reasons, H is an electrolyte. It's an electrolyte because it is a what? It is a salt that breaks apart into ions, Na+, and the acetate ion, which of course is given to you in table E. Okay? But it is also, okay, a basic salt. Okay? Why? Because the conjugate base that's negative, as I talked about earlier, has an ability. This conjugate base that's negative, that's not part of the top 5 acids I've given you, has an ability to what? To ionize water. Okay, so what we have here is we have an acidic salt, and I'm going to write it in red. All right, it's a salt, but it's an acidic salt. So for 2 reasons, okay, that is a definite, okay, electrolyte. All right, even without the definition of an acid and base, it is still any salt that's soluble, okay, is clearly. But I'm going to write it in red to show you that it's an acidic salt. Okay, all right, ammonium chloride. Ammonium chloride. Well, ammonium chloride is another soluble salt. Based on our solubility rules in table F, ammonium chloride breaks apart into ammonium and chloride. And so that makes an electrolyte. It's a soluble salt. Free ions. You have to have free ions in solution. So, of course, that is an electrolyte. However, okay, is it an acidic, basic, or neutral salt? Well, I know the chloride ion is a conjugate base of hydrochloric acid. I know hydrochloric acid is a very strong top 5 acid on that table. So the chloride ion must have no ability to pluck a proton from water to reform the acid. That's the reason why it is strong. So this is a spectator. Now what does this do? Well, wait a minute. Isn't this the conjugate acid of NH3? Right? This is NH4+. NH3, we learned, is a decent base because it can yank what? A proton off of water. And it produces NH4+. Wow, so this has an ability, okay, if this is a weak base, because it's not a group 1 ion and a group 2. Remember, the strong bases are all the group 1 ions in the hydroxide, or a group 2 ion and a hydroxide, even though they're dibasic, okay? So if this is not a strong base, it's a weak base, which makes it what? A pretty strong conjugate acid. So NH4+, okay, has an ability to donate that proton, let's say, to water and make H3O+, which decreases the acidity. So yes, this is an electrolyte, choice I, well, only because it breaks apart into free ions. However, I'm writing it in red to let you know that it is an acid, okay, or acidic salt. Drop that salt in water and the pH drops, because in that salt you've got a conjugate acid that has an ability to protonate water. Okay, next one, silver chloride. Look at, I'm even hinting that it's a solid. So silver chloride, I'll circle it in magenta. Okay, this is a precipitate. Precipitate has no free ions. So the J is not an answer. Okay, now K, I'll take a HSO4 negative is a what? Is a ion. So HSO4 negative and HS negative are definitely clearly going to be electrolytes because they are already ions in solution. They're already free, so clearly they are. But let's define them more. HSO4, okay, is this an acidic or a basic salt? Okay, or ion, I should say at this point. Because if I had, and I don't, but if I had sodium hydrogen sulfate, right, I could say, is that a basic, acidic, or a neutral salt? And I would hope that you can recognize that this HSO4 is a conjugate base of H2SO4. H2SO4 is a strong acid, sulfuric, right? Sulfate, 8 becomes ic, sulfuric acid gives off a proton to water, let's say, and it becomes HSO4, negative. So this hydrogen sulfate really has very little ability to accept protons, either from the solution itself or water, or ionized water. So it has really no ability, okay, to pull an H from the water. And you may understand why. Look at the charge density here. You have 6 atoms, okay, with a total of a -1. So it's hard for it to pull a proton away. In any case, that makes this, okay, yes, it's clearly going to be an electrolyte, but I'm going to write it in black, K, to recognize that, let you know that if you had it in a compound, it would be a neutral salt. It has no ability to accept an H. And, well, the problem is that this is also has an ability to donate an H2, so I can't quite go there. But I will say that it is definitely going to be a salt that, or it's definitely going to be an electrolyte. It's not going to be a basic salt, and it probably has some acidity because it can give off its H+. So that's one to think about there. Moving on, okay, we have the HS negative. And when I think of negative charged compounds like this, I just think of conjugate bases. Hey, what's the conjugate acid of HS negative? Well, you've guessed it, H2S. Okay, if the name of this is binary, so it's hydrosulfuric acid, and it gives off a proton, and it becomes HS negative. Okay, now the question is, well, is this a strong acid? Well, no. Okay, so this is a what? Pretty significant base. All right, so I'm going to go blue for basic here, and I'm going to circle this. And it's of course going to be a electrolyte because it is a free ion, but I'm going to write it here as a base, so you know that that ion is definitely basic. It has an ability to pluck a proton from water because the conjugate base is significant. Why? Because it comes from a weak acid. Weak acid, strong conjugate base, low Ka, higher Kb. All right? So that's how I evaluated all of these. Okay? Now, which acid is the best electrolyte? Well, if you look at all the acids I figured out, either from salts or from compounds themselves, well, obviously it's going to be A because A is the only one that is the strong acid. We only have one strong acid, so its Ka is large or very large or reaching infinity. So nitric acid is a strong acid. So that's the one that has the largest Ka. Okay, so which acid is the best electrolyte? The one with the largest Ka, and that's A. Which acid has the largest Ka? Same question. Okay, and that's of course nitric acid. Which chemicals would create an acidic pH? Now I'm asking you who your acids are. All right, and that's very clearly the ones we've just defined, okay, as A, nitric acid, B, CO2, okay, G, the complex of iron and water, okay, H, that's the salt of acetic acid. Oops, not that one. I think I might have that one. That's a base. I'm not sure why I have that one in red. Made a mistake, I see. You guys should have told me as I'm doing this. Okay, yeah, this is definitely a base, sorry. So H, I put red. Sorry if I confused you and you were screaming at me, but clearly that is a basic salt. Ooh, bad Grodsky. So that's not acidic. Yeah, this is acidic. Okay, so I, acidic salt, and that's it. Who has create a basic pH. Which chemicals? Okay, that's my F negative. That's my C. Let's make that blue. So it's going to make that C, D. My barium hydroxide is a strong base. E. All right. H. Okay, as I incorrectly had it red. Okay, and that's it. Oh no, I'm going to put K, but if you didn't put K, it's okay. That guy is well, it's a conjugate base of an acid. So we're going to say no. Okay, and HS definitely. So L. All right. Okay, which salts are neutral? They have conjugate acids, and bases come from strong acids and strong bases, which have no ability to go in reverse. So my neutral salts, okay, are my F, okay, which is a KNO3. And KNO3 was a salt made from what? Potassium hydroxide plus, okay, nitric acid, HNO3. That made nitrate ion, terrible conjugate base, and the K plus, okay, terrible conjugate acid, okay, and that's what made the KNO3. Which chemical is the conjugate base of sulfuric acid? Conjugate means what's left over of the same chemical after it acts as an acid. So sulfuric acid is H2SO4. It gives off a proton. What's left over? HSO4 negative. Don't forget the charge. If you get the charge, it's wrong. Chemicals are amphoteric. Amphoteric means they can act as an acid and base. Okay, I believe HS is the best example here. HS negative. If you look at table L, you'll see that HS has the ability to act as an acid and donate a proton, and it would make a conjugate base of -2. But it also has an ability, okay, HS, to yank a proton away from water to make the hydroxide, because it has a you'll see. So now, how do I know that? Well, the best way to answer that is look at your table L and see that HS is on both sides. So getting back to table L, you see that HS negative is the conjugate base of the hydrosulfuric acid, and you also see that HS can act as an acid. So you see it's on both sides. Now, if you look very carefully, okay, you'll also see the conjugate base of HSO4, okay, can act as an acid. And you may say, Mr. Grodsky, this is on both sides. I'm sorry, you see HSO4, not HSO3, but you see HSO4 on both sides. So you might say, well, that must be amphoteric too. And that's kind of tricky, because even though it's listed as a conjugate base, we know that because it's a top or a strong acid, this really doesn't go in reverse. Okay? But this does have a significant Ka. So if you notice, HSO4 has a pretty high Ka compared to all the other acids. So HSO4 will not be listed as amphoteric. But if you had a salt with HSO4, wouldn't it be acidic? If you had a hydrogen sulfate, sodium hydrogen sulfate, yeah, you darn right it'd be acidic. So you need to look at your Ka sometimes to help you through this. So going back to my definition here, I kind of left this blank, but in truth, okay, that's why this is a really tough assignment. That's a good review though. This is an acidic, okay, ion. So I should actually add K here. All right, because this is a pretty decently, it's a weak acid, but of all the weak acids, it's the stronger of the weak acids listed here. So if you were screaming at me, hey, what about that one? Now you see I was waiting to do that. I definitely made a mistake here. Okay, apologize if I wrote that incorrectly, but if you lasted along with me in this lecture, you'll see that. All right, so I'm pretty much done here. I think that you can figure out the rest here. I have the key. But identifying the crux of this lecture was to help you review how to discern between acids and bases and salts that are mixed in, and using table K, and that's what this was about. Hopefully this helped. Okay, please use the key to guide you through the rest of this. I believe this is the hardest part of this assignment.